In New Jersey, an inferno rages at the heart of a community.
The whole road was blocked with fire trucks and ambulances. We knew it was a big deal.
In the UK, a brand new hospital on the edge of catastrophe.
If those beams will collapse, the entire building is going to collapse.
Tragedy in New Zealand as a volcanic flood takes down a crucial rail bridge.
The force of it took the carriages and washed them down the river.
And disaster strikes in Spain on a major dam construction project.
This raging torrent was so powerful it wiped out everything and everybody in its path.
With big bills, even the smallest fail can trigger a huge disaster. From miscalculations to misunderstandings, or just plain bad luck. These catastrophes are every engineer's worst nightmare. With everything they do, engineers try to plan for any possibility. But sometimes, catastrophe takes them by surprise. Like this story in New Jersey, as disaster struck a chemical factory.
I don't know if they were aware of just how dangerous this was. It sounded like a 10,000-pound bomb.
Spreading fear across a community.
They were just surrounded by black smoke. People who were forced from their homes.
As a catastrophic chain reaction took hold.
Once this material catches on fire, it all catches on fire, and it is too late.
This disaster forced an industry to change.
Lodi, New Jersey, sits just west of the Hudson River, with a population of around 30,000 people. Philip Toronto is the former mayor.
Well, Lodi is a small town. It's always been a middle-class, blue-collar type town. A lot of families. And as a kid growing up, you had to behave yourself because everybody knew who you were, and they knew your parents. So you couldn't get away with much in Lodi.
As well as being family-focused, Lodi has a long history as an industrial hub.
A century ago, it was home to a massive textile mill and dye works. And over the years, more factories moved in with homes and schools for the workers and their families.
We had a lot of companies that were using a variety of chemicals that are not necessarily the safest things to have. So we employed a chemical engineer as an inspector so that we know and have an inventory of everything that's in the borders of Lodi.
For decades, a chemical and pharmaceutical plant sat on this plot. At its heart, a massive blending machine. Aaron Moment is a professor of chemical engineering.
Most commercial products that we use in our homes, as well as in industry, are blends of components that are mixed together.
The process sounds simple, but it comes with risks.
Blending is often extremely dangerous. Chemicals should always be treated with respect. They can behave in unplanned ways that lead to accidents.
Despite the hazards, the factory and Lodi residents were close neighbors for more than half a century. But the harmony wouldn't last forever. Friday, April the 21st, 1995. Lodi's mayor was warming up on a cold spring morning.
As I was having coffee here that morning before I went downtown.
But around 7:45, Philip's morning routine was disrupted by a violent blast.
It sounded like a 10,000-pound bomb hitting. And when I went outside, I could see this black plume going up. We knew something pretty terrible had occurred.
News photographer David Adonato was on call.
I knew where I was going just by seeing the black smoke that was coming up from the fire itself.
The mayor learned from his emergency team that the blast had come from the chemical and pharmaceutical factory.
He briefed me immediately that we had an explosion. We don't know the extent of it. The site is under the fire. They were dousing it.
It was a very significant fire. The whole road was blocked with fire trucks and ambulances, EMTs, and there were people being taken away to the hospital. It was pretty crazy. We knew it was a big deal.
By the time I was there, it was a surround and drown. Just keep pouring water on it.
There were cherry pickers and firefighters throwing water down on top of the factory, and they were just surrounded by black smoke.
This factory was huge, and no one knew what chemicals were caught up in the Inferno. It must have been terrifying.
I recall a huge cloud of smoke coming up, and we were concerned at the time that there could be some sort of chemicals that would cause health issues for the residents.
As the fire raged and the smoke billowed, 300 people were evacuated from their homes.
The homes are literally across the street. How scary is that? Your possessions, the place that you feel comfort, you have to abandon it.
By early evening, the blaze had been tamed.
They had the fire under control, but unfortunately the damage had been done.
With the fire and smoke in retreat, investigators found that 4 factory workers had been killed in the blast. Another was seriously injured and in hospital.
I had to go over, and these people are waiting there and tell these families that their loved ones were lost.
Tragically, the 5th worker later died from his injuries. And yet, the death toll could have been much worse. A late spring snowfall had swept through the area, forcing people to stay at home during the week.
They closed the schools that day for a 3-day weekend. Thank God they did. The high school is on that side of town, so there would have been traffic, there would have been children, there would have been parents when this thing exploded. It was just incredible. We didn't have any civilian injuries. We were very lucky we dodged a bullet there.
This is a huge deal. The families that live here are affected by it, the factory workers who were affected by it. I mean, this was a business that supported the community. So it's a huge deal whenever something like this happens.
The disaster rocked the tight-knit community and made national news. Everyone wanted to know what could have triggered such a massive explosion.
When it's a chemical company and then you have an explosion, you have to figure everything that's in inventory, and now it's mixing. What's the result?
Investigators knew that on the day of the accident, around 4 tons of chemicals were being blended. Professor of Chemical Engineering Aaron Moment studied the disaster.
They were manipulating thousands of pounds of powder in a very large dryer to be used as a recovery agent for gold, specifically in the field of mining.
The mix included 800 kilograms of powdered aluminium.
Aluminum powder is used in paints and solar panels, but it's also a key ingredient in fireworks, missiles, and rocket boosters.
Each of the chemicals being mixed was stable at room temperature, so the question was, what had gone wrong? In the hours leading up to the disaster, workers had noticed strong odors.
Almost everybody in the factory could smell that something was wrong, and the smells were very sharp and pungent, like rotten eggs.
Operators opened the mixer to investigate.
They did observe pools of things reacting in the dryer that indicated to them that things were not going according to plan and there was a problem.
At the time, workers didn't know the source of the trouble. But investigators later concluded that something unwanted had made its way into this chemical cocktail.
There was one unexpected, seemingly harmless ingredient that caused things to spiral out of control: water.
Inside the mixer, the water reacted with another chemical used for dyeing or bleaching, sodium dithionite, which contains sulfur, explaining the rotten egg smell.
Well, water is such an issue because the sodium dithionite reacts with water to release gas and heat. And as the heat is released, the reaction accelerates. Pretty soon, you're operating at a temperature that's way in excess of what anything was planned. In addition, you have around this aluminum, and you have the presence of a lot of oxygen as an oxidant. They knew that they had a potentially explosive situation.
Investigators were unable to pinpoint how the water entered the mixture. But with the increasing heat and pressure, the chemical reaction started to accelerate.
It's not clear if there is anything that you can do, because there is a point at which, once the aluminum is reacting, it's probably too late.
Inside the vessel, the chemical cocktail was now in a runaway reaction.
A runaway reaction is exactly what it sounds like. Once the reaction starts, it snowballs, and there's nothing you can do to stop it.
Yet, workers did make a desperate attempt to avert disaster.
The operators hoped that dumping the mixture out of the vessel would somehow stop the reaction, but they were wrong.
As the blender was unloaded, the powder caught fire, and the whole mixture ignited.
They tried to shut it down, but it was too far gone, and it exploded.
The factory was almost completely destroyed in the fire. The city of Lodi had no desire to risk a repeat of this disaster, so no plans were made to rebuild it.
You wasn't going to let something that could be that explosive in a town on a main street that only by the grace of God didn't have school that day, or we would have had a bunch of casualties.
The ripples of the disaster forced the industry to look long and hard at safety.
The primary thing that's happened since this time frame is a robust process safety program that's been implemented within the chemical process industries in the United States to prevent these type of accidents from happening in the future. That's a really big positive change since 1995.
This explosion helped spur the creation of the Chemical Safety Board, with its ongoing mission to help protect people and the environment against future disasters like this.
While Lodi's citizens will always remember the tragic accident, the community is proud of how it handled the catastrophe.
You know, I've never forgotten it, and I don't ever want to go through it again. Watching the town come together and its volunteer fire department, ambulance corps, emergency management, police, it was incredible.
In big engineering, every structure is in a constant battle with the elements. But sometimes Mother Nature doesn't fight fair. Like this story in New Zealand, as a railroad catastrophe struck on Christmas Eve.
There were no warning signs.
The noise from the river was horrific.
A disaster that flattened a bridge and derailed a train.
This was the dead of night. Nobody knew the bridge was down.
This tragedy was the worst rail disaster in the nation's history.
The whole of New Zealand was shocked, stunned, and in mourning.
New Zealand's North Island is home to some of the most dramatic scenery in the world. At its heart, the central volcanic plateau. Civil engineer Walter Rushbrook works in this remote region.
Central volcanic plateau is a very high alpine type environment. You've got steep valleys that run off the mountains. It's very active landscape. It's been basically forged by large volcanoes.
The views might be stunning, But the jagged landscape is a nightmare for installing infrastructure.
From an engineering perspective, building roads and railways through here, really challenging as a combination of sort of weak, highly erodible ash combined with hard rock and boulders. So when it comes to, say, building bridge piers and things like that, it's very, very hard to get a good foundation for your structures.
Yet as far back as 1885, engineers rose to the challenge, building a railroad from Auckland in the north to Wellington in the south.
It took over 20 years to plan, survey, and cut more than 700 kilometres of track through the wilderness.
This part of New Zealand was literally the middle of nowhere. This was pioneering stuff. They were hauling everything into the area, and it was all done by hand. Very, very manual, demanding work, and they were breaking new ground and trying to create the railway line.
As the railroad nears the central volcanic plateau, the tracks pass near the slopes of Mount Ruapehu.
From the ground, Ruapehu looks like a mountain, but it's actually a stratovolcano. And at the top, there's a giant crater that's filled with a lake of warm water.
This crater lake feeds the Whangaehu River, which flows south to the sea. For more than 100 years, trains have crossed the river thanks to a bridge at Tangiwai. But this isn't the first crossing here. Christmas Eve, 1953. Late in the evening, an express train with 285 passengers and crew was nearing Tangiwai on its journey north towards Auckland. Debbie Clooney is from the National Army Museum, Te Matatoa.
The train was full of revellers and family members happy to be going to Auckland to spend time with their friends and family over the Christmas break.
Up ahead, the Whangaehu River was running dangerously high and had damaged the bridge. Remote and rural, only a passing postal worker was witness to the precarious situation.
The postal worker ran to the track and attempted to warn the oncoming train with just a flashlight.
The driver quickly realized something was wrong.
He applied the brakes, dropping sand onto them, which helps to slow the wheels down a lot more quickly.
But it was too late. The locomotive hurtled onto the damaged bridge, which catastrophically collapsed into the raging river, taking the train down with it.
The carriages were tossed by the water, and the force of it took the carriages and washed them down the river.
As word of the crash spread, both authorities and locals alike rushed to the scene. Just a boy at the time, Bruce Thompson arrived with his mother.
We came out and the noise was horrific from the river. The first piece of wreckage we struck was carriage 3. It had been virtually cut in half.
Rescuers scoured the mangled wreckage for survivors.
My mother, she'd trained as women's auxiliary during the war, and she stepped in to help whatever she could.
As dawn broke, the true scale of the disaster became clear.
There was carriage way down, right down the river. Carriage 2 was across the stream. Carriage 6, of course, was across the other side of the river.
Although over 100 passengers were rescued, many more were still missing.
But they were looking for bodies, were searching the rivers, and they went from here down. And this carried on for quite some time.
When the recovery operation finally came to an end, the death toll had climbed to 151 people. After learning the news, the entire nation was in mourning on Christmas Day.
The whole of New Zealand was shocked, stunned. Virtually everybody would have known someone who had family on that train, because at that stage New Zealand wasn't a huge population.
This combined to be the deadliest railway accident and one of the worst natural disasters in New Zealand's history.
Within days, the government had launched an inquiry to discover why the bridge had failed.
In the Southern Hemisphere, Christmas falls at the height of summer, and there hadn't been any major storms recently. So the big question was, Why was the river flooding so badly?
A clue came from hikers who had climbed the nearby volcano Mount Ruapehu a few days earlier.
There were two trampers who had been up on the mountain and they had noticed a change in the colour of the crater lake. The temperature appeared to be rising and also the lake level was getting higher.
Geologists travelled to the volcano and discovered that the southwestern side of the crater wall was missing, and the lake was no longer there.
Up on the mountain, a large plug of ice was becoming loose on the crater lake edge, and in the evening, just before the train approached, the plug came out and a huge wall of water came down.
The flood that emptied down the mountain was a volcanic phenomenon known as a lahar.
A lahar isn't an ordinary flood. It's a mix of water, rock, mud, and anything else it sweeps up. It's more like concrete than water.
That explained where the flood had come from, and when the lahar reached the steel and concrete bridge down below, the mass of debris was 6 meters deep and struck with monumental force. Ian Heapy is a historian.
When the lahar hit the bridge, Pier 4 and Pier 5 were both ripped out. Probably 130 odd tonnes of concrete ended up approximately 80 metres downstream, and there's not an earth-moving machine in New Zealand even today that could have done that. So it gives you some idea of the total power of it.
The flow rate was almost 3 times more than the bridge piers were designed to handle. There was no way the bridge could survive when the train thundered onto it.
Although engineers knew of the risks from a lahar, they had no idea just how powerful the raging torrent could be.
The scale of lahars is as unpredictable as the volcanoes that caused them. And back in the 1950s, they were even less well understood than today.
In the aftermath of the disaster, it was clear that a replacement bridge would have to be able to withstand the worst that the crater lake could throw at it.
The new bridge consists of a steel through-plate truss, and the reason for that is they wanted a very long-span bridge to minimise the number of piers in the river, so there's only one pier in the river now.
This lone river pier was tailored to withstand the forces of a lahar, with a foundation set deep down into bedrock.
By placing them very deep and very securely, it also provides a lot of lateral load support. So when, say, a lahar is pushing hard on it, it's less likely to fall over.
With the new bridge in place, the next task was installing a way of detecting lahars long before they struck.
Even with modern engineering, protecting against lahars is a huge challenge. So early warning systems are essential to ensuring that nothing like this could ever happen again.
Today, a system of detectors is in place from the mountain down to the river.
Up on the mountain, there was seismographs and acoustic sensors that we could detect the lahar really early on, so it gave us 2 hours warning that something was on the way.
In 2007, the preparations paid off when another massive lahar rumbled down the mountain. The flood of rocks, mud and water lasted nearly an hour.
So it was a bigger lahar than 1953. The warning systems all successfully triggered, so we had lots and lots of notice. The line was made safe, and best of all is the bridge survived supremely well.
Great news for modern travellers on the line. Thanks in part to the new safeguards, the tragedy is unlikely to be repeated. But it will never be forgotten.
We have a memorial service. We think of them then. And every Christmas Eve, the train comes through and slows down and throws a wreath off into the river. And that's part of our ceremony.
In big engineering, every step is worked out in meticulous detail. Any change in plans can have dramatic consequences. Like this story in the UK. The troubled construction of a landmark new hospital building.
This project seemed to hit problem after problem.
They found asbestos, there was cracked concrete.
Problems that were leading toward devastating results.
They discovered not 2 beams that had faults, but 8.
There were real concerns that these cracks could have led to catastrophe.
Liverpool in northwest England owes its success to the River Mersey, with swift access to the shipping lanes of the North Atlantic.
Liverpool thrived thanks to its working docks. In the mid-20th century, like many industrial cities, it fell on hard times. But in recent decades, it's experienced something of a rebirth.
In 2014, construction began on this state-of-the-art 11-storey building in the city centre, a new wing for the Royal Liverpool Hospital. John Corbett is a city tour guide.
The Royal Infirmary is our main hospital. It's part of 300 years of medical development in the city. It's in the centre of everything. It's where people go for outpatient treatment and also for surgery and long stay treatment as well.
Paul Jones is a sociologist based in Liverpool.
This hospital is a crucial public service for the people of Liverpool. It's somewhere that the city vitally needs.
The distinctive, jagged-edged structure was predicted to cost around £500 million.
Hospitals are eye-wateringly expensive things to procure and build.
That cost is in part down to the multiple functions the structure must serve.
The building might look complicated on the outside, but that was nothing compared to the inside. Modern hospitals are a warren of rooms with different roles, from ambulance bays and scanning suites to patient wards and cafeterias, each with their own engineering challenges.
There's much increased sort of commercial space of cafes, of shops, of non-clinical spaces for patients to hang around in. So healthcare thinking and hospital design has changed a great deal since the 1970s.
But 2 years into construction, the high-profile project was heading way over budget and off course. December 2016, less than a year before the building was scheduled to open, problems started to surface.
The contractors kept putting the actual completion date off. There was asbestos discovered in parts of the building which had to be removed, bad weather halting exterior construction, and also cracking concrete. These postponed the completion of what should have been a prestigious new hospital.
Most concerning was the cracking concrete. Structural engineer Luigi Disano knows the case.
2 cracks were identified on a beams that was located on the lower floor, which was a sign of possible failure that could take place. So when in a structure you detect cracks, it's always a warning that you need to investigate further.
But before anything could be done, the project was hit by another setback.
Midway through construction, it turned out that the original contractor had serious financial problems, and it looked like the hospital was going to be left in limbo.
To fix some of these technical problems would have taken a lot of time and a lot of money, and effectively the developer ran out of both.
Our hospital was not going to open anytime soon.
The city desperately needed the new hospital facility, but before construction resumed, engineers investigating the cracked beams discovered that the situation was worse than they had expected.
At the point when new contractors took over the construction, the new developers found 8 cracked beams, up from the original estimate of 2.
Luckily, at this stage, the building was still empty. But reports suggested that under the load of a full and operational hospital, 5 of the 8 beams could have failed.
Concrete is hugely versatile. That's why you see it in everything from dams to bridges and hospitals. But if it's overloaded, it can fail suddenly. So these cracks had to be taken very seriously.
If it detects cracks at the lower floor, that's an indication, is a very important sign of warning, because it means that if those beams will collapse, the entire building is going to collapse.
Investigators dug deeper to expose the real extent of the problem and what needed to be done to fix it. The first step was to understand just how serious the cracks were.
When concrete sets, it shrinks, which can cause cracks to form. Up to a point, small cracks might not be a problem. The question is how widespread they are and how big they might eventually become.
The size of the crack can be different. If they are small enough, they are protecting the steel that is inside the beam. If they are large, then they can be an indicator of failure occurrence, and then we need to intervene.
The location of the cracks on the beam is also critical, as Luigi demonstrates with a beam loading machine.
That is what happens when you have a heavy weight in the middle of a beam. So the beam will start to deflect, and this one, as you see, is a very, very small crack that is progressing within the concrete. So another one is forming here, and as you see, as the load progresses, new cracks are forming along the beam.
At this size, cracks can potentially be filled, and if the excess load above is reduced, the beam can be returned to service.
This is a level of crack size so that we can intervene and repair them, because what will happen by removing the load, they will disappear. So this is a level of acceptable size of crack.
But if the load causes cracking beyond this acceptable level, it can trigger a total failure of the beam.
That's the formation of the rupture of the beam, where concrete is collapsing. And then you see that this is not acceptable. The concrete has reached the crushing capacity, and you see that the failure is now being spread, so the beam is not able to carry any further load. Luckily, this has not happened in the Royal Hospital, so that we were able to repair it, because this stage was never reached there.
Although the damage was caught before there was a serious failure, some beams were deemed too weak to do their job. The question was, why?
One possibility was a change in weight distribution between the design and construction phases.
The formation of the cracks was primarily attributed to possible extra load that was applied at that location, and it was not designed for.
Engineers always add safety margins, but if something changes between design and construction or going into operation, then the calculations could be out of date.
The extra load could have been due to a new location of heavy machines that were located at that floor. And what happens when you start to load the structure, then it can show some pathological cracks, which means that the crack go beyond certain limits that are not acceptable.
With the risks identified, the next challenge for the construction team was how to fix the beams.
By the time this problem came to light, the structure was pretty much complete, so any solution would have to be literally bolted on to whatever was already in place.
So it was very complex then to design an adequate solution for repairing the structural damage that was detected.
Here, the fix involved hundreds of tons of concrete and steel that would reinforce any weak points without overloading the floors below.
The solution that the engineer proposed was to have an extra frame within the existing structure that had to be maneuvered within an existing structure without interrupting the functionality of the remaining floor.
Finally, in September 2022, the new building, now structurally sound, was ready to receive patients. It might have opened 5 years later than planned, but for Liverpudlians, it was well worth the wait.
At last, the people of Liverpool have a world-class hospital to call their own.
In big engineering, problems can lie hidden for years before revealing themselves. But sometimes they strike while construction crews are still hard at work. Like this story in Spain, as catastrophe ripped through a massive dam construction project.
Vast quantities of water came crashing down in minutes.
The sudden failure of a crucial safety feature.
Que empezó a tocar la sirena. Fue un reventón.
Yendo el agua a un sitio donde la gente no podía escapar.
This was one of the deadliest industrial disasters in Spain's history. In western Spain lies one of the nation's best-kept secrets, Monfragüe National Park. This paradise, where the Tagus and Tietar rivers meet, boasts the largest and best-preserved Mediterranean forest on Earth.
Monfragüe National Park is one of the most important conservation areas in Europe. It's home to an amazing array of wildlife, from wildcats to otters, but it's best known for its huge population of vultures.
Anthropologist Manuel Trinidad Martín has been studying the area for years.
El Parque de Monfragüe es sin duda una de las zonas naturales más importantes de Europa. Tiene alimoches, tiene, una fauna impresionante.
The idyllic area has all the natural resources for wildlife to thrive. But the remote region's human residents required infrastructure to provide steady supplies of power and water. So in 1959, work began on a major double dam project. One big dam on the Tagus River and a smaller one nearby on the Tietar.
Entonces aquí en Monfragüe se crearon dos pantanos, cuyo objetivo era el aprovechamiento hidroeléctrico y también crear regadíos.
Although the dams would create two separate reservoirs, they would join forces to produce power, thanks to a giant tunnel linking both with the hydroelectric turbines.
This was a huge project. 2 dams across 2 rivers, with one power plant between them, built into the ground.
Not only would people get much needed water and power, but with the 7-year construction came thousands of jobs.
Durante esos años venían de todas las poblaciones de la zona y también de otras partes de España a trabajar y venían con todas sus familias.
But before the dams went into service, this massive project would wreak havoc on the region, on a scale that no one could ever have imagined. Friday, October the 22nd, 1965. Despite unseasonably bad weather for this part of Spain, the whole project was nearing completion, with both dams nearly full.
Fue un otoño muy lluvioso. La presa estaba prácticamente en su nivel más alto y que era una mañana de mucha niebla.
Hundreds of workers were on site. Benito Martos was in the design office when suddenly an alarm rang out.
Porque empezó a tocar la sirena. Pues sabíamos que era un accidente.
In the town of Salto, just downstream, Jaime Canelo, then 15 years old, heard the siren.
Me eché a correr, sabíamos que estaba la cosa muy mal. Todo el poblado estaba intranquilo.
A torrent of water was gushing through the tunnel leading to the turbines.
Ahí había cientos de hombres trabajando y en muy pocos minutos, pues, se puede imaginar.
Fue un reventón.
The construction site had been transformed into a war zone.
Y donde un
señor... estaban las maquinarias, las máquinas excavadoras eran como barcas de papel.
No one yet knew what had happened, but dozens of workers were missing, including Benito's father.
Yo me puse muy nerviosa, porque en ese momento no sabía nada de mi padre. Mi padre estaba en una zona de peligro.
Thankfully, no one in town was killed. But at the dam site, although Benito's father survived, many workers, including Jaime's cousin, had perished in the flood. The official death toll was 54. But many believe Spain's leader, the dictator Franco, had suppressed the true human cost.
La realidad es que perfectamente se pudo llegar a los 100 fallecidos muy posiblemente, ¿no? Fue una tragedia enorme, o sea, fue algo muy triste.
The loss of so many people left local communities devastated and wanting answers. Just what had caused this terrible tragedy? Much has been lost to history, but officials do know that on that day, engineers had begun testing the dam's water release spillways.
After nearly 6 years, construction was almost finished, so they began filling the reservoirs to assess the spillways.
Although testing was standard procedure, some believe that it was done with too much water in one of the reservoirs. Jaime Canelo lived nearby.
El domingo ese antes del accidente, me subí por encima del muro, echado de barriga en la plataforma que ya tocaba el agua. Con lo cual, no se podía retener más agua.
The reservoir was only supposed to be filled to 85% capacity before being tested. This went way beyond that.
Y no estaba al 85, que estaría por lo menos al 90
Sí,
ya.
cuando...
Mínimo. Que la presa rebasó el límite de lo que estaba permitido que soportara.
The dam's excessively high water level likely exacerbated an existing problem, with a floodgate which sealed off a channel leading to the turbine tunnel. Professor of Civil Engineering Miguel Ángel Municio explains.
Sabemos que se rompió una compuerta, que esa compuerta estaba en un canal, en ese canal conducía a un túnel que estaba en construcción, donde había gente trabajando.
This gate was a crucial safety feature, designed to keep the tunnel dry while workers were inside.
El embalse tenía un nivel alto, la compuerta lo que hacía era cerrar el paso al agua al canal que conduce a lo que sería después la central hidroeléctrica a través de un túnel. Ese túnel estaba en construcción, entonces esta compuerta cerrada, que era su función era estar cerrada para proteger a toda la gente que estaba trabajando en la obra.
But instead of holding back the water, the floodgate failed catastrophically.
When the gate gave way, more than 50 workers were trapped with no way out.
Based on eyewitness accounts, many believe this vital floodgate was incorrectly fitted. Benito Martos worked on the project.
El problema fue que esa compuerta se colocó
demostramos,
mal.
Con los años pudimos demostrar de que la compuerta la pusieron mal.
If the gate was installed backwards, then the excess pressure from the full reservoir wasn't pushing the gate closed, but rather forcing it open.
A massive amount of force pushing against an incorrectly fitted temporary floodgate. This was only likely to ever go one way.
This one failure was enough to cause dozens of deaths, and yet resulted in little permanent damage to the project.
La verdad es que no fue la presa lo que falló, de hecho la presa está, el muro sigue estando. Lo que falló fue la mala colocación de la compuerta.
Testing the dam by pushing it way past its capacity before it was even finished proved to be a catastrophic mistake.
In the aftermath, with the dam structures unharmed, construction was able to continue, while the Franco regime began to look to the future.
Se echó un tupido velo, como se suele decir, por encima, echa una manta por encima y aquí no ha pasado nada.
Nunca hubo ningún culpable, no se encontró ningún culpable. Un accidente de ese tipo en que habían fallecido tantas personas.
2 years after the disaster, the Twin Dam project was complete and generating electricity thanks to the enormous power it had so tragically demonstrated. And 4 decades later, a memorial was finally erected in Monfragüe National Park to recognize and remember those who lost their lives on that tragic October day in 1965.
At the time, the government hoped to keep news of the disaster quiet. But for the people of Spain, this is one tragedy that will never be forgotten.